So today's handout is a little bit thicker, just to kind of space out the questions and to make sure you have space. But we're going to talk about the rest of the rational function stuff. So last time we talked about just about the holes and how that's different in a X-Intercept and how that's different in a vertical asymptote. So you have more detailed notes on that part from your other page. So I don't know that we need to keep rewrite those exactly word for word, but I'm just going to give a quick summary here. And I'm going to suggest that if it bothers you that some of your work is on one page and on another page, then you might copy it over to here too. So the ones we already talked about, and I'm not going to be much focus on today because you should feel okay with those, is holes. It's when you had an X value that makes the numerator and denominator 0. X-intercepts occur when Y equals 0 and a fraction equals 0 if you can make the numerator equal 0 only. And then we had vertical asymptotes that we located, and those are X equals a number, and they occur when you try to divide by 0. So if there's a number that made just the numerator 0, X-intercept, just at the denominator 0, vertical asymptote, and if it made both 0, it was a hole. Now again, this is not very detailed, so good chance that you want to copy over what we wrote down on the top of your page last time here so that you have it all in one nice neat space. But for me, I feel like I know those pretty well, so I don't feel like I need a super long explanation on those. Okay, we also, to be able to graph these, because you can see that given an equation, we're going to ask a bunch of stuff about it, and then we need to be able to come up with what the graph looks like without just plugging it into our calculators. So definitely one of the easier things is X-intercept, Y-intercept. Y-intercepts always have an X value of 0. So set X equal to 0 and solve for Y, just like you have been doing since Algebra 1. If you want to Y-intercept, plug in 0 for X and solve for Y. So those usually work out nicely. We need to know how to find horizontal asymptotes. And those of you doing calculus next year for rational functions, big reason why rational functions are important for calculus is because of this horizontal asymptote stuff here. Okay, and then for horizontal asymptotes, there's 3 things that could happen, 3 rules that we could apply. Okay, you have to compare. So if we had some generic function here, if I call the degree of the numerator n and the degree of the denominator m, we compared those degrees. Biggest exponent in the numerator to biggest exponent in the denominator. Sometimes we have a number out front here, sometimes we have a number out front there. I'll call them generic A and B. Well, when the degree of your numerator is bigger than the degree of your denominator, you do not have a horizontal asymptote. If your degree of your denominator is bigger, your horizontal asymptote is Y equals 0. And if your degrees are equal, your horizontal asymptote is Y equals leading coefficient over leading coefficient. So whatever that number A is over that number B. Okay, so a couple of those can kind of make sense if you think about them in a certain way, so I'll try to point that out to you today. But at the end, you really just want to know those 3 rules and be able to apply them. Yeah.
So for the degrees, it's like the largest number.
Correct.
Place.
Yeah, like if this was x to the 3rd, and then there was plus some x squares and plus some x's and plus a constant, none of that stuff matters. The degree is the biggest exponent. So we're just focused on that. Okay, we have domain, which I'm not going to go much in because we've been doing this all year. Describes the x values of the graph. So there's some numbers that just don't exist on the graph, so those have to be taken out of the domain. The domain describes what x values you can have. And then finally, the last one is slant asymptotes. And then we'll look at what this stuff looks like and actually practice using it, help you ingrain this in your brain. But slant asymptotes, this is what we typically call it in America. I think most of the rest of the world call them oblique asymptotes. So like, you know, if you looked at something online, it's likely to say oblique asymptote, but it's the same thing. And its equation comes from, you have to do long division. That's why we practiced that last time. And your equation will be y equals the quotient only. So ignore any remainder that you have. Okay, and not everything has a slant asymptote, so we don't want to have to do long division all the time. We only want to do it when it's necessary. You only have to do this when the degree of the numerator is one more than the degree of the denominator. So most of these don't have a slant asymptote. So we certainly don't want to do long division and waste our time most of the time. Check the degrees. If the degree of the numerator is one bigger than the degree of the denominator, it will have a slant asymptote. And then to find its equation, we'll do long division. And the equation will be y equals whatever the quotient is. The remainder has no effect on the slant asymptote. Okay, so for me, I kind of like this one place where we're summing up all the different things that we need to talk about. So kind of like last time, you know, how I describe find Y-intercept, you might want something more detailed. You might want to squeeze an example in here, but we'll come back and do that as you see necessary. Okay, so let's go to question 1 and let's actually start looking at these graphs and see if we can predict what these graphs look like. So let's first start off with the ones we did last time. Those should be the easiest, only because you've had practice on them. X-Intercept, vertical asymptote, and holes. Both of these require you to know what makes the numerator 0 and the denominator 0. So typically we factor that. So it looks like the denominator has a GCF of 3. And then what's left over factors as an x plus 3 and an x minus 2. So it looks like there's nothing that makes the numerator 0. 1 never equals 0. And the numbers that make the denominator 0 would be 2 and negative 3. 3 never equals 0. This doesn't give us another one. Okay, so there's no numbers. Again, I'm not focused on this part too much today because I feel like you should have had some practice here. No numbers that make the numerator and denominator 0, so no holes. There's no numbers that make just the numerator 0, so there's going to be no X-intercepts. And there's 2 numbers that make just the denominator 0, so those will be vertical asymptotes. Okay, so holes are kind of a pain to find. They take us a minute to do the algebra behind it. But if there's not one, or if there is one, it's kind of nice because it does help you figure out your graph. Same thing with X-intercepts. We kind of hope that we have some because it gives us some information about our graph. Vertical asymptotes. Asymptotes are always graphed as dashed lines. You need to graph this like this because that's the way to show that you know that there's going to be spikes in the graphs. Same thing with slant asymptotes later. We'll graph those with dashed lines as well. Okay, I like to come back and do domain at the end personally. Let's do Y-intercept. So this was the first new thing we wrote down in your notes today. Y-intercepts always have an X value of 0. So just go to your function and plug in 0. You get 1 over 0 plus 0 minus 18. So negative 1/18. So super close to 0 below the x-axis. Okay, and then for our little table, that's a point. Okay, horizontal asymptotes. This is where you compare the degree of the numerator to the degree of the denominator. If the degrees are equal, you put leading coefficient over leading coefficient. If the degree of the numerator is bigger, it doesn't have one. And if the degree of the denominator is bigger, it's y equals 0. Well, the degree of this is 0. There's no x's. The degree of this is 2. You're comparing the biggest exponents here. So when the degree of the denominator is bigger, it's y equals 0. There's really no shortcut for just knowing those three possibilities. Either the degree of the numerator is bigger, smaller, or equal. And it would be this, this, or this. Okay, so it's an asymptote as well. So we can graph him as a dashed line. And that helps us know what's happening at the ends of our graphs. Okay, slant asymptote. We would do long division, and it's going to be y equals whatever the quotient is. We would ignore the remainder, but only if the degree of the numerator is 1 bigger than the degree of the denominator. That's not the case here, so I don't want to do that because it doesn't even make sense. Okay, so for domain, now I have my graph here. Poles have to be taken out of the domain. Vertical asymptotes have to be taken out of the domain. Those are x values you can't plug in. So it looks like I can plug in everything over here. So everything from the far left until you get to -3. But we can't plug in -3, so that's a parentheses. And then we can plug in all of these x values from -3 to 2. Not including -3, not including 2. So parentheses. And then it looks like everything over here is fair game too. So x values 2 and bigger will also be part of my graph. So they're part of the domain. Okay, so I'm going to erase this, but just to help you see this, this is describing my graph's going to exist in all of this area. This is describing that it's going to exist in all of those x values. And this is describing that it's going to hit all of those x values. Okay, the only x values that are taken out are -3 and 2. Don't include -3, don't include 2. Okay, well, for the rest of our graph, it just depends on the question. Depending on what you have up here, the closer you are to being done with this graph. But for us, we need to find a few more points. So that's what the table is for. And so I'd recommend plugging in whatever you think's easiest. I'm probably not going to plug in a half. It doesn't look like a half is going to be easy to evaluate, but maybe plug in 1. If I plug in 1, get 1 over 3 plus 3 minus 18. Which would be -112. So also super close to 0, but a little bit bigger than that one. Okay, I would probably try to plug in -1, and this is going to come together faster than you think. We don't need a ton of points. Usually we need 3, 4, 5 points. If I plugged in -1, this would still be 3. -1 squared is 1. This would be -3. And then minus 18. So plugging in -1, we get 1 over -18. Okay, let's try maybe one more, and I'll tell you how this falls together. Okay, if I tried to plug in, obviously the more points you plug in, the more confident you should be about your graph. But if I tried to evaluate at -2, this is just going to be a touch harder, but we've got to try it. 3 times -2 squared would be 12. 3 times -2 would be -6, and then -18. This would be 6 minus 18, which would be another -1/12. So lined up with this guy. Okay, so I don't have enough information to make my graph perfect, but I do have plenty of information to be ready to sketch this graph in. So what you can see from doing just a few points, if it's got to connect these points, go ahead and connect them. You can see a little bit of curvature there. And then the big key that unlocks the rest of the graph is understanding how it behaves around asymptotes. On vertical asymptotes, because you can't plug in the number 2, as you get really close to plugging into, your number gets either really big, it goes to infinity, or it goes really small and it goes to -infinity. Based on this going down, I know that this is going to keep going down, and since it can't ever be this, it's going to shoot down on this side. And if it goes to -infinity on this side, it's going to go to +infinity on that side. So in a perfect world, I'd find another point over here, but I know that. And then same logic right here. Going from right to left, I can see that this is slightly going down. So it's going to continue going down. And at a vertical asymptote, it's going to spike. So based on its trend, it's going down on this side, so up on that side. And then what the horizontal asymptote tells us is what the y value approaches on the ends of our graph. As x gets really big, it's going to approach y equals 0. And as x gets really small, it's going to approach 0 on that side as well. Okay. So let's load up the calculator program here and graph it and confirm that that is what it looks like. And this is really the best way to learn to check your mistakes on these problems. So if you don't have your own calculator, I'm going to ask you to borrow one of mine here when I have you practice them. Okay, so we've got this, then like a U shape, and then another one of these guys. And the x values are a little bit different. Like I only went out to -5 and +5. So if you wanted to look closer, you have to go in here and adjust these. But just kind of eyeballing it, it looks fine to me. Okay, you see how that's our graph? So it is a lot of information. And in some problems you do some things and not other things. But between knowing those characteristics and plugging in a few more points, we can predict what this rational function is going to do and how it's going to behave. Okay, anything about question 1 that I skipped over too quickly? Anything you want to add to that? Okay, then let's look at question 2. Even if you feel, again, just to be clear, even if you feel like, man, I remember all of this from Algebra 2, again, this one didn't even bring up slant asymptote. It also didn't have a hole. Like the next question might have a slant asymptote, it might have a hole, but it may not have horizontal asymptote. Like you got to practice several of these before you can really feel like you're confident. Okay, the ones we did last time were X-intercepts, vertical asymptotes, and holes. So we need to know where the numerator equals 0 and where the denominator equals 0. Doesn't even require factoring this time. Okay, does this question have any holes? Good, because there's no number that makes the numerator and denominator 0. Does it have any x-intercepts? Which one? 2 or 4?
2.
Okay. Any number that makes just the numerator 0. So that's a point. And then vertical asymptotes are vertical lines that make just the denominator 0. And those show up as dashed lines. Now, again, if you don't know those rules, that seems like a lot right now, but I did very little work there. Once you know the rules, there's very little work to be done on these questions. Or they should get quicker at least. Okay, and then the new notes. So we did this last time, so that's why I'm not focusing on these too much. But if you're struggling with those, when I have you practice them, please ask some specific questions. But of our new notes today, Y-intercept always has an X value of 0. So just plug in 0 like you do any other point, and you get -2 over -4, or a half. There's another point on our graph. Okay, again, you can do these in any order you want to, but I like to save domain for last personally. Horizontal asymptotes, we have to compare the degree of the numerator to the degree of the denominator. Looks like the degrees are equal. Degree is 1, degree is 1. So that is this case. When these are equal, your equation is y equals leading coefficient over y leading coefficient. So our leading coefficient is 1 for the numerator and 1 for the denominator. So y equals 1 over 1, which is 1. Okay, so that's a dashed line. That helps us understand what's happening at the ends of our graphs. And then slant asymptotes, we would do long division, and it would be y equals the quotient only, ignore the remainder, but only if the degree of the numerator is 1 bigger than the degree of the denominator, which is not true here, so we get to skip that again. Okay, so now I know all the numbers that are taken out of my domain. Looks like this is the only x value that's not allowed to be plugged in. So I'm going to be able to plug in any of these x values, which would be everything from the left up to x equals 4. And then everything to the right of that, so everything from 4 to infinity. It's a fancy way of saying you can plug in anything except for 4. Okay, and usually we need a couple more points. In the last question, honestly, if it was a test, I probably would have plugged in 1 or 2 more points to be sure. On this question, I think I'm ready to graph it already. And the big key here, so that you don't have to plot a million points, is you need to understand how it behaves around these asymptotes. Obviously, if it goes through these 2 points, you can connect them. If it's slightly going down right here, you can expect that it keeps going down. And this vertical asymptote is going to be a spike in the graph. So this is either going to go to negative infinity or positive infinity. But there's no reason for it to change direction here. So if it goes to negative infinity on the left, that means it'll go to positive infinity on the right. And then for this horizontal asymptote, the horizontal asymptote tells you what y values it approaches at the ends of our graph. So it gets close to 1 on the far left, right, and close to 1 on the far left. I didn't need any extra points, or I don't believe. Well, I'm sure of that, but what you would want to do to help check your work is to graph it, scan the graphs, and make sure that they look the same. This and this. This and this. So this technically, I guess, was a little bit more like that, but that's still pretty accurate. It's not going to be 100% accurate unless you plug in a million points, but it was pretty close. Okay. Let's look at one more together so we can see a little bit more of what's unique, and then I will ask you to start trying parts of question 4. Okay, so if we start off with the ones from last time, I know I need to know what numbers make the numerator and denominator 0. And unfortunately, this one requires some factoring. Looks like a GCF on the top. to see that it equals 0 at 0, -2, and 3. GCF on the bottom. To see he equals 0 at +2 and -3. -3 never equals 0. That doesn't give you another one. Okay, so if there was one number that was in both lists, that would be a whole. Doesn't look like that happens. If there's any number that janks just the numerator 0, those are going to be X-Intercepts. So it looks like this guy has 3 X-Intercepts, which is good for us because that means our graph's going to be easier. We got more points. I'm going to go down here and put those points down. And then if we have any numbers that make just the denominator 0, those will be vertical asymptotes, which are vertical lines. So you need to say X equals on those two. And graphically, those help out a lot too. We get the dashed lines, but more importantly, we know how they behave around those dashed lines, which is how our graph usually falls into place right before we finish. Okay. And then the new stuff today, Y-intercepts are when X is 0. So you plug in 0 for X, you get 0 minus 0 minus 0 over 0 minus 0 over 18. 0 divided by 18 is 0, which that should make sense, right? If there's an X-intercept at the origin's not just an X-intercept, it's also a Y-intercept, but we confirm that algebraically. We can do the horizontal asymptote rules, where we compare the degree of the numerator to the degree of the denominator. If the degree of the numerator is bigger, it's 3, and this one's 2. And that's when you don't have a horizontal asymptote. Again, as long as you know those 3 rules, there's very little work there. Okay, I now know all the X values that get taken out. It's just these 2. So I should be able to have all of these X values, -infinity to -3. I should be able to hit all of these X values in the middle, -3 to 2. And then I should be able to hit all these X values to the right of 2 to infinity. So again, it's kind of like saying you can plug in everything from -infinity to +infinity, but skip -3 and skip +2, because those give you division by 0, so they can't exist. Okay, and then slant asymptote, we have to do long division, and it'll be y equals the quotient and ignore the remainder, but only when the degree of the numerator is 1 bigger than the degree of the denominator. Is that true in this case? All right, so this guy's going to have a slant asymptote. This is the first one that's had a slant asymptote. So I don't know. I like a little bit more space for these, so I'm going to do it down here. But we're trying to divide this into this. Now, unfortunately, this one's going to have a couple fractions. That's going to make it a little bit harder, but it's nice that we have just reviewed the long division algorithm. So this times this needs to give me that. So how many x's do I need? X times x squared would give me the x cubed, but I need it to be 1x cubed. So what number or what fraction can I multiply by -3 to get 1? Negative what? 1/3. Good. Negative times a negative is positive. 1 multiplying by 1/3 is like dividing by 3. So again, the fraction part's a little tougher, but it's okay. Okay, and then we had to multiply to all the other pieces too. So x times x would be x squared. Negative times a negative would be positive, and 1/3 times 3 would be 1. And then x times no x's would be an x. Negative times a positive would be negative. And 18 times a third, again, timesing by a third is just like dividing by 3, which would be 6. And then we want to subtract all of this. So we're going to change the signs and add instead. These we saw last time go to 0. Now when we combine these, we get minus 2x squared, and these go to 0. So it looks like we can go one more time, because there is something here times negative 3x squared that gives us negative 2x squared. Well, I've already got the x squared, so I don't need that. I would say this is a positive, because a positive times a negative gives me a negative. If I multiplied by 1/3, 1/3 times 3 would be 1. So if I want it to be twice that size, 2/3. So now let me multiply that. 2/3 times this would be positive times a negative would be negative. 2 times 3 would be 6. Divided by 3 would be 2. And times x squared. Also multiply it to this stuff, which would be minus 2x. And let's see, 18 times 2/3 would be like 18 times 1/3, which would be 6 times 2, which would be 12. Change the signs and add. Okay, looks like our remainder is 2x minus 12. Your remainder doesn't just have to be a number. I was going a little bit quick there at the end, and I could potentially even maybe have a sign wrong here. For long division, that's important, but for slant asymptotes, remainder is not part of your equation. That is what we were searching for. This guy, our slant asymptote, will have the equation y equals what the quotient was. Negative 1/3 x plus 2/3. So long division, y equals the quotient, ignore the remainder. Okay, well, it's an asymptote, so let's go ahead and graph it. It's in the form mx plus b, so it looks like the y-intercept would be at 2/3. Its slope is negative 1/3, so down 1, right, 1, 2, 3. And asymptotes should be graphed as dashed lines. Okay, so for vertical asymptotes, we know how it has to behave around them. It's going to shoot up on one side and shoot down on the other side. For horizontal asymptotes, it tells us what's going to happen at the end of the graph. And then slant asymptotes do the same thing. It tells us what is going to approach at the end of the graph. So I would be tempted to maybe plug in -1 here. Again, you usually need a couple more points. But if I tried to plug in -1, my numerator is going to look like this, which would be 6/18, which is 1/3. So it's about right here. And again, I didn't know that was the point to get, but I'm just kind of more interested in what's going on there. And the reason why I wanted to know what's going on here is because I want to know some direction here. Like, I know my graph's probably not flat between these points. Now that I've got this one more point, I know there's a little bit of curvature here. And now you need to be very careful that you pay attention, because if you blink, the graph's going to be completed. Now that I know this is going down and it's approaching this vertical asymptote, it must be shooting down on this side and shooting up on that side. For the same logic, from this point to this point, he's trending down. So he's going to continue to trend down. And then when he approaches this vertical asymptote, he's got to either shoot up or down. Well, he's going down, so he's going to keep going down. If he shoots down on this side, then he's going to shoot up on this side. I had this X-intercept from earlier, so I know he has to connect there. And then our last piece to the puzzle, again, the ends of your graph for a slant asymptote work the same way as the ends of your graph for a horizontal asymptote. It has to approach this line, but not cross it. So the further out right you get, the closer it's going to get to that line. And then over here, if this is coming up, at the end of his graph, he's got to approach this line. So he must be turning and going that way. So you can achieve the same thing by plugging in a ton of points, but understanding how it behaves around those asymptotes saves us a bunch of time. Okay, I really don't want to graph all of these today because it does kind of slow us down just a bit, but I will go ahead and plug this one in. Okay, does that look like our graph? And then sometimes it's even nice to graph like the slant asymptote. It looks like it's right here. That's this line. And I said it was y equals negative 1/3 x plus 2/3. Negative 1/3 x plus 2/3. You don't have to graph it also, but it's kind of nice if you do because you can see how it squeezes in. Like this gets really close to it, and then this gets really close to it on the ends of the graph. That's what that's telling you. Okay, so now I think you've seen all of these parts. So I do want you to start to practice these to really see what you've caught on to and where your focus needs to be. I don't think you, well, maybe if you remember some of this from last year, you can just kind of dive into it, but I want to section it off for you. So for question 4, I'd like you to practice these 3 things first that we did last time. Practice them. We'll check and confirm. I'll give you a couple more to think about and try. We'll check those and confirm. Then I'll ask you to try to graph it. We'll check it and confirm. And then should be done with that question. Okay. Anybody need to borrow a calculator from me today? You should need a calculator in the next couple minutes, but at some point I want you to check by graphing and making sure that they look the same as what you anticipated it to look like. And depending on which skills you kind of caught on to, you might be quicker at some parts of this, and your neighbor might be quicker on different parts. So I'm going to be pretty patient here at first. But if you've got those 3 things done and you're just waiting, you could start one of the next parts. Or if you're not sure if you could do those parts, you could maybe look at question 5 and do some of the parts that you think are easier and start chipping away at the next questions. Okay, so the longest part of those questions is you do need to know what numbers make the numerator 0 and denominator, which means you need to factor both sometimes. Sometimes they're not needed to be factored. But you need to be slow and careful with your factoring because that could mess up all of your work here where you had to maybe start it over. So any number that makes just a denominator 0, like -1, should be a vertical asymptote. And so on our graph, x equals -1 will be a dashed line. Any number that makes just a numerator 0 is how you get an X-intercept. So the only place that should touch the x-axis is 2, 0, and that's a point. And any point we can get helps our graph fall into place. So got that guy done. And then holes, the x value occurs for any number that makes the numerator and denominator 0 at the same time, like -3. And then the y value, which is typically the part that students forget sometimes, you have to plug this not into the function because you get 0 over 0. Not into the factored function because you still get 0 over 0. You have to plug it into the reduced fraction. Let these cancel out and then plug it in. That would give us -5 over -4 times -2. -5/8. Let me double check my arithmetic there. Yeah, that sounds right. Now, while that doesn't seem super helpful because it doesn't hit that point, we will graph this as an open circle because we do know that it hits the points right before it and the points right after it. So to graph this correctly, we do have to graph -3, -5/8. Should be about right here. And we want it to be an open circle to show that it's not hitting there. Still going to help us with our graph though in a minute. Okay, so those three are what we kind of chipped off from this big set of stuff that you need to know last time so that that would be just a touch easier. But now I'd like you to think about from the new stuff today, try your Y-intercept, consider horizontal asymptotes, slant asymptotes. Try those three, please. And of course, try to see what you know without looking at your notes first. But it's better to look at your notes than be completely stuck. Okay, so once you're really comfortable with those rules, that should have been about 4 times as much time as you needed. Y-intercepts have an x value of 0, plug in 0 for x. 0 plus 0 minus 6 over 0 minus 12. Negative 6 over negative 12 is a half. Slant asymptotes is the long division process, but only if the degree of the numerator is 1 bigger than the degree of the denominator. Because that's not the case here, that should be a 5-second question. Horizontal asymptotes, you have to compare the degree of the numerator to the degree of the denominator. If the degree of the numerator is bigger, you don't have a horizontal asymptote. If the degree of the denominator is bigger, it's y equals 0. And if they're equal like this, it's y equals leading coefficient over leading coefficient. So y equals negative 1/4. Okay, so you can't graph a slant asymptote if it doesn't have one, but you can certainly plot this point for Y-intercept. You can certainly graph this horizontal asymptote, a horizontal line. Horizontal line. And then you can plug in more points. Well, let me give you 30 seconds here. See if you can figure out what you think the rest of the graph will look like without plugging in any points, and just to see if you get some of it correct. Just do a light sketch of what you think the graph's going to look like. Okay, so since you've got these 2 points, you connected them, you can see going from this point to this point, the line's going up. So understanding this behavior of this vertical asymptote, if it's going up, it's got to go up on this side, which means it goes down on this side. Understanding the horizontal asymptote helps you know what numbers it approaches at the end of the graph. Tells me that this is going to get close on this side and close to that line on that side. But how do you deal with this? I think you're saying the right thing. I can't hear you very well.
It went up on the right hand.
Okay, this is going down, yes. How does this connect to this? Or does it? Okay, remember, a hole is the one instant that it doesn't hit. So it really hits the points before it and the points after it, right? So really, we know that. And then the horizontal asymptote tells me that it approaches that on the left. Again, if I graph this on my calculator to check, that's always a good idea when you have a calculator. But remember, it's not going to do a good job of showing you that hole. So we had some workarounds there, but I didn't need to plug in a million points, but I did have to know how to find X-intercept, Y-intercepts. Finding this hole will be asked of you, and it helps with our graph. Vertical asymptotes certainly help us fill in our graph quickly, and you'll be asked for those as well. And then horizontal and slant asymptotes, sometimes they don't have one or the other, so it's not always a ton of work, but I guess we do prefer not to have slant asymptotes, but you got to practice that sometimes to be able to do it. Okay, so that was question number 4. So now this time on question 5, now I'm going to ask you to just try the whole thing, except one tip here. There is a negative sign out here, so it might be a good idea to just bring it up near the 4. But otherwise, I'd like you to just take what, oh, we didn't do domain, did we? Sorry. Domain is a way to describe all the X values that you can hit. So I'm tempted to say, based on the past questions, I can hit everything until an X value of -1, and then I can hit everything after -1. Is that correct for this question? Okay, then what's the other X value we couldn't plug in? Right, we can't plug in -1, but notice we don't have a Y value for -3 either, so you have to be careful. So I can plug in all of these guys, -infinity to -3, Then I can plug in all of these guys, -3 to -1. And then finally, I can plug on everything to the right of that, -1 to infinity. It's kind of nice to have the graph done before you try to answer domain. There's no y value here, so that it's not part of the domain. X doesn't exist for x equals -3, and x doesn't exist for -1. Okay, so for question 5, I would like you to just kind of chip away at, start off with whichever ones you find to be the easiest first, and then move towards whatever you think is to be the most difficult. So you should be able to answer hopefully a handful of these without looking at your notes on the front page. But once you get stuck, read your notes on the front page, and then go back and try to answer that. And then throw all that stuff on the graph, maybe get another point or two. Graph it in your calculator, and if your calculator looks correct with what you graphed, then it's probably fine, and you can start moving at your own pace a little bit more. Now, of course, when you look at the notes on the front page, to help you with one that you feel less comfortable with, make an effort to try to actually remember it, so that on the next question, you don't have to look at your notes as much. You should just be winging yourself off the notes just a little bit more from each question. Yeah. For those of you that are interested, how this comes up in calculus, really the first big calculus unit that we do is limits. And with limits comes continuity, and if a continuous function, continuous or not. And so when it's not continuous, sometimes there's different types of discontinuity. And so sometimes there's things like infinite discontinuity, which is when your graph goes to infinity and negative infinity. And then there's things called removable discontinuity. So you have to know the difference between a hole and an asymptote, and why a function has a hole sometimes and an asymptote sometimes, to know what type of discontinuity that you have. Okay, I'm going to give you about 2 more minutes for question 5. Again, if you're finished, please graph it and see if it looks correct. If it doesn't look correct, it might give you a hint about what you may have done wrong. But then, finished or not, I'd like to go over this one with you to maybe help you verbally with some of your corrections. Okay, so again, this is where it gets kind of tough because I've got to say all the rules, and hopefully you know half of them already. But you can go in any order that you want. So as you move forward, always start with what's easiest, and then slowly inch your way to the ones that you're struggling with or have not picked up on yet. So I'm just going to go in order from now on, because to me it's all about the same. Y-intercept is when x is 0, -4 over 0 minus 0. Well, what is -4 divided by 0?
Undefined.
Okay, so when you have 0 divided by a number, you get 0. When you have 0 over 0, anything could happen. That's when we have a whole. And if you try to divide by 0, that's not possible. So we can't divide by 0, so that doesn't exist. There's not going to be a y-intercept in this question. Now, at first it might be like, well, that's weird. How's that going to look? The rest of this should be consistent with that before we're done. So x-intercepts are numbers that make the numerator 0, but -4 never equals 0. So no x-intercepts. By factoring the denominator, you should see heat equals 0 at 0 and 3. So that is 2 vertical asymptotes. Okay, and that's why it couldn't have a y-intercept. It's because that there's a vertical break in the graph there. It's not allowed to exist there. So now that makes sense why that's not working out. Or if you force the number there, like if you thought it was going to be 0 or something, this information conflicts with each other, so it kind of helps you catch your mistake. Okay, wholes would be numbers that make the numerator and denominator 0, but nothing made the numerator 0, so there's not going to be any wholes. I'm actually going to skip domain. I know I said I was going to do these in order, but horizontal asymptotes, you have to compare the degrees. The degree of the numerator is bigger, it's none. The degree of the denominator is bigger, it's y equals 0. If the degrees are equal, it's leading coefficient over leading coefficient. The degree of this numerator is 0 because there's no x's, so the degree of the denominator is bigger. Slant asymptote is the long division process, but only if the degree of the numerator is 1 bigger than the degree of the denominator, which isn't the case here, so I get to skip that too. Okay, so there's my, I didn't really get any points out of all of that, but here are my asymptotes, which will help after I find a few points manually. But I can see now the graph or the domain. I'm going to hit all of these x values from the far left to 0. I'm going to hit everything between 0 and 3, but not include 0 or 3, and everything to the right of 3. Okay, so then the only way you can really move forward, some questions we didn't need to get any additional points, but this one we got to have some point on our graph to even have an idea of which way we're going. So I'm going to just try to plug in this easiest thing that I think I can evaluate, maybe like 1. So -4 over 1 squared minus 3 times 1 would be 2. So at 1, there's a point at 2. Again, you don't have to find that specific point, but you got to start finding some points. Doesn't look like 2 would be too bad. It'd be -4 over -2, which would also be 2. So that's probably not flat. It's probably like going up and then down or down and then up. Maybe plug in 4. At 4, it looks like it's -1. Okay, and to me, I think that's probably going to be pretty close. If this was a test and I felt like a lot of points were on the line, I'd probably plug in a couple more points. More points is always better and safer. But now that I think I'm pretty close to the end of this graph, this is going to approach this on the right. The fact that it's going this direction means this one must be headed down. If it goes down on this side of the vertical asymptote, it must go up on that side of the vertical asymptote. It has to go through this point that I found. It's got to go through that point that I found, so he must turn around. And if he does, he goes up on this side of the vertical asymptote, which means he goes down on that side of the vertical asymptote. I really probably prefer to have a point here, so this is a little more accurate. But I do know he's going to approach this on the far left. So those are going to connect somehow. So again, it just depends on how accurate I want to be. If I get the exact y value when x is -1 or x is -2 would definitely be more helpful. But if you graph that, if it doesn't look right, then it gives us a hint about what else we should have considered. And I'm graphing this on my own calculator off to the side. And he looks good. So that's how I would know to move on. What's right? Okay, so any particular part of that I'm just going over too quickly that you guys need to ask about? Okay, you do not have to finish this whole packet for homework. That's probably too much. But on the agenda, I said I want you to do 3 more of these. So if you'd please do questions 6, 7, and 8. If you would star those or write that on your assignment. I would also highly recommend, before you put this away, because we've got about 6 minutes till you're dismissed, if some of your notes in this box on the front page aren't detailed enough, or you'd like them to be worded in a different way, or you want more words and less math symbols, then by all means, go back and add to it or replace what I had you write down. Whatever's going to help you is what I want you to have down. So eventually I will ask you to finish this, so it will not hurt you to move past, but you need to do at least 3 of these as practice outside of class, please. If you don't have your own calculator, I guess you could use like Desmos to graph and check, but make sure you're checking by graphing before you consider a question complete.